Now we're on the air. Good afternoon, this is Dr. Ray. Today I want to go over how to use floating point instructions using Linux. And now it's time to switch to screen sharing. Well, I would like to, but I can't make the button work. This computer had a blue screen of death at 12:35, and I've been trying to get back in gear since then. I also had, for some reason, Google Plus. My previous version of this was Dr. Ray introduces floating point instructions, and when I went to try it out, it was repeating the previous session. And now it won't do screen share. I will entertain very briefly before I give up. I haven't planned on doing stand-up or sit-down comedy. I don't know if I can make this behave or not. Screen share for Hangouts was hiding from me. So I may have a chance after all. Well, I see something, but it doesn't seem to be correct. Let's see. I will try again. Okay, now it looks correct. So I've started with an empty program called float.asm. I'll probably use doubles, and I'll repeat my habits. I'll start with a main, and I'll put a frame statement in here. Two parameters to main. At the moment, I don't need any, local variables. I think I may write a function that uses 3 parameters. Now, to save time, I will use data that's in the data segment. And I will use DQ, and I'm going to use floating point arithmetic. How about 1.5, 1.6, 1.7, 1.3, oops, I need a comma, 1.3, 1.4, 2.1, 1.8, and I have 10 numbers in here, 1.6, 1.25, 1.3. Now I've got enough numbers that I don't really know what the average is, but I will write some code to compute the average. Before going any further, I'll make sure that this thing is correct syntax, just to cut down on the confusion. Yes, it appears to be correct syntax. You can see the assembly data, and you can choose double format, and we see the numbers as I've entered them. All right, that's good. So now I would like to do load effective address into RDI, the first register parameter, and I need the address of X, and I want to move into ESI a 10 for the number of elements to work with, and I will call average. Average. Push RBP and move, oops, I got a little too far to the right. RBP, comma RSP, and frame command. There are two parameters to this function, and I think I'm going to need maybe a local variable. Maybe I can handle everything in registers. Let's see. I shouldn't need to call any functions. All right. So I've got 10 numbers. Frame size. Forgot that in the main routine. See if I forgot it. Yes, I did. It's going to be subtracting 0, but I like to be a creature of habits. If I could develop good habits, I would do better. Good habits aren't so habit forming, though. All right, so I've subtracted the frame size, and now I need to decide which register I would like to do this work in. And I'm going to return the average in XMM0. What I'm going to have to do is add all the values up. So then divide by 10. That sounds like it would be pretty easy to do with using XMM0. So I think we can do several choices. We can sub SD, subtract scalar double, XMM0, comma XMM0. And if you want to learn about instructions, with a recent copy of the EV code under assembly in here, I've now got instructions documented, so we can look at the floating point instructions, and we can look at the syntax for subtract scalar double. And scalar means there's one of them. The alternative to that is subtract packed doubles. And with packed doubles, if you use sub PD, you'd be doing subtract a pair of numbers in one of the XMM registers from a pair of numbers in another one. But for the start, we're going to be doing just scalar doubles. So you can subtract XMM0 minus XMM1, and the result goes in XMM0. This is kind of handy. There is even an XOR-PS. I don't think there's an XOR scalar singles, but if you do pack singles, you'll be doing XOR of all 128 bits of the XMM register. So that would be an alternative way of zeroing it out. All right. All right. So here we are. We've got the value there, and we need to have us a register, an integer register, to be the count register. So the next one in line would be RSI. Excuse me, RSI is in use. So we need RDX. So let's do XOR EDX, comma EDX. And then we're about ready to do the top of the loop. And we have a question: should we consider this to be something where we're guaranteed to have more than 0 elements or not? I'm going to not test to see if I'm divided by 0, but I know I'm testing with 10, so I'm not really going to test it very thoroughly. So doing a test at the top of the loop isn't really necessary if you're assuming there's at least one element in the array. So assuming at least one element in the array, then we want to add the next element of the array. Add scalar double, and we're going to add to XMM0, and we want to use the array, which is the address passed in RDI, and we want to add to that 8 times RDX. All right. So using 8 times, when RDX is 0, we're going to get the first location. When RDX is a 1, we'll get RDI plus 8, and it will go on like that. All right. So we increment EDX, and then we want to test to see if we've completed all of them. So we compare EDX versus ESI. Now, if we make it to 10 exactly, then we know we finished. If it's less than 10, that would be if we increment it and we have 1 and then we have 2. Each time we're going to be, by the time we get here, the number in EDX is the number that we have read, or the number that we've added to XMM0 so far. So we need to do a jump less than to top. Once we're done with that, we're ready to divide, except that the number we want to divide with is in RSI, and we need to convert it to a floating point number.
The house tried to keep out all the water, but water got inside and ruined everyone's everything. The house thought she loved the family down, but just didn't think it could happen. He told the house they would take better care of it. Oh.
I think I'm getting some feedback from probably John Heath. Anyway, let's see if I've got the convert instructions documented. They're not in the floating point instructions. I don't see a convert. I may have left that out. All right, I believe the instruction is CVT for convert, and it would be integer to scalar double. Let's see if I'm correct.
$19.
And we will use XMM1 as a place to put the result, and we can use RSI as the value to do. And the next instruction is divide scalar double. Dividing with floating point is simple. All the arithmetic operations are simple. They are done the same way. Divide XMM0 by XMM1 and put it in the result. You don't have to have a double size register with 2 of them like you did with division of integers. Instruction expected after label on line 33. So CBT I2SD is not correct.
I can go fishing with my dad.
Please call or go online right now.
And send $1.
Your call will give a child a gift of hope this Christmas.
Please call and go online now.
I don't have
Fox News Channel is on Sirius XM. Listen live
that way.
14.
Let's see.
Welcome back to the real story today. Police helicopter at the center of a very frightening crash. That's this. Chopper responding to another crash in Santiago, Chile. The fire truck quick gets delayed. The helicopter flips and begins spinning, as you can see in this video. It explodes into flames. The pilot critically hurt. Another officer also injured. So Turkey used to almost always be considered an ally for our nation when it came
Well, it's got convert,
in recent
packed
years.
integers, convert.
Well, now could be that the U.S. and Turkey are working on a deal for joint military action against ISIS. The U.S. wants to use Turkish air bases to launch attacks across northern Syria.
I think it's SI to SS or SD. Let's try again.
Direction. Joining us now, Rear Admiral John Kirby, the Pentagon Press Secretary. Welcome to the real story today, sir.
Ah, that came out red. Red is an indicator that it is an instruction. And I hadn't done that in a while, so
On the fact that
it probably indicates that I did forget it from the report or from the documentation. So let's test this code. Push RBP, and now the frame looks fine. We've got RDI 60288 and RSI as a 10. Now we want to step into the average function. Push RBP, subtract the frame size. We have no local variables, probably won't need them. Subtract XMM0 minus XMM0. So now we have a 0 in the first one. And we want to add that to this one. Let's see. The first number should be a 1.5. So switching to the floating point registers, let's see if we get 1.5. Yes, we do. Then we increment EDX, compare it against ESI, jump less than top. Hey, that's correct. The next number we want to add is 1.6. So we should get 3.1. See if we can make this thing skip the loop. Oh, gee. Let's catch it here. We'll run it again. All right, now we're ready to do the conversion. RSI has a 10 in it. Let's see if we get a 10 in XMM1. Yes. And then divides scalar double. We get 1.555. All right. So we've now computed an average. And in general, for all of the arithmetic operations, add, subtract, multiply, and divide, the way they differ is like here, add, pack, double, add, pack, singles, add, scalar double, add, scalar single. They all have these 4 little extensions to the generic name. And for a packed single, that would be 128 bits used as 4 floats. For packed double, it's 128 bits used as 2 doubles. and scalar just means one of them. And they chose scalar because they could have used packed and single, but they used single for single precision and D for double precision. Being a C or C++ programmer, I would have preferred D and F. So you could use single, double, and single float, but that's not what they chose. So scrolling on down, I've only got 3 of these div instructions. Div pack double, div pack single. I've left out div SD. There's also maximum and minimum. And you can see in here I've got several varieties of max and min in here. I'm assuming that's showing on the screen. I'll verify it. I think that's the way it's worked in the past. Yes, more or less. I have it drugged slightly off. All right. And minimum works the same way. It's got 4 varieties in its naming. So you can do min, scalar, single, min, scalar, double, min, pack single, min, pack double. So you can use a floating point register with a floating point register. There are 16 in total, so you can use XMM0 through XMM15. And you can use just a label if you've got a label in the data segment or the BSS segment. You can use a register. You can use like a label plus an index, or a register plus an index register with a multiplier. Oh, that should be an 8. There's an error in my documentation. So going on further, we've got multiply, pack, single, pack, doubles, single, double, single, scalar. All right. And then there's subtract. All right. So having done average, it would be natural to want to learn a little bit more about the data. You could have 1.55 and have no real indication of the spread of the data. So I'm going to take the intuitive approach for the spread of the data and compute standard deviation by taking the deviation from the average and subtracting. Take a value minus the average, so like 1.5 minus 1.55, then take that and square it. If you take all these squared deviations, add them all together, take an average, and then take a square root, you get effectively the standard deviation, with one minor exception. With standard deviation, you're supposed to divide by n minus 1. I'm not real sure why n minus 1 is so nice for dividing by, but that's the way they do it. All right. Now, I think I will put the average and standard deviation in this place here. So let's move. Let's see, if we want to move unaligned pack double, that's the instruction for moving the floating point value. Move it from XMM0 to RBP plus local 1. And then we want to do load effective address, RDI, and it in fact has not changed, but it's a fairly good habit to go ahead and do it again. And then move, and the RSI has not changed either. And we're going to do 10 numbers, and we have an average, and I'd like to use move unpacked, unaligned, not pack double, scalar double. Oh. And it's move scalar double. Move scalar double. May as well align it nicely. And I'd like to move this average to XMM1. This is more or less what a compiler would do if it were not optimizing your code. Then call standard deviation. See who I'm seeing. Oh, it's Glenn. Howdy, Glenn.
Hello.
Now going down, the code for standard deviation is going to resemble average, so I may as well copy this code and modify it. Where's my cursor? Got two averages in here now. All right. So for standard deviation, there were 3 of these values, and XMM0, let's see. Oh, I made an error here. I should be passing this in as XMM0. Now, my code could work fine by itself, but if I'm going to write code that's compatible with C, I need to follow the rules. So XMM0 would be the one for the first floating point parameter. I don't want to zero that out, so I want to do my next summing in XMM1. So what I need to do is how about move scalar double into XMM2. So now I've got the value, and I want to subtract into XMM2 minus the average, which was passed in as XMM0. And then I want to square the number. So we do a mul scalar double XMM2 comma XMM2. And if we want to get a sum of these squared deviations, then we'll do add scalar double XMM1, and I didn't type that too well. Add XMM2 to XMM1, and then we've got all these squared things done. This time, instead of dividing by n, which was in RSI, I want to divide by n minus 1. So how about if we do a decrement operation on ESI before we do the result here. Right. And we divide this, and we want to convert it and put it into a different register. How about XMM2? That's going to, XMM2 will be n minus 1. XMM1 is the square, the sum of the squares of all of them. After we divide it by n minus 1, we have the approximate average of those square deviations, and now a square root. Now, we can take advantage of the fact that we have, I believe, the on this computer, these AVX instructions. Let's see if it works. And if you use the form of these instructions that begins with a V, you can use 3 operands. So you can have a destination and then one source and another source. So these two would be the same as before. If it were division, it would be this one divided by that one. So we can get it transferred into the proper location with this operation. 1 instruction rather than 2. All right. Redefinition of top. I've got top in both of them, so the easy way to get rid of that problem is to name them dot top. Dot in front of a label gives you a local label, and it belongs to the previous global label, like average is a global label, so put dot top there. Now we've got 2 dot tops. There's no challenge with that. Line 34, it's not happy with me. Oh, I did a sub. Imagine that. Sub SD. All right. I will proceed to skip past the call to average, and we get 1.555, and then we want to load local 1 in there, and then get the address of, get the address of the array, and then put a 10 in RSI. Then we'll put the average in XMM0 and call standard deviation, and I'll step into that code. All right, subtract scalar double. So XMM1 got a value of 0, RDX is 0. Then we're going to get a value into XMM2 from RDI plus 8 times RDX. That sounds correct. And then subtract that minus, that minus 1.555. We get a negative, fairly small value. We square that number and then add that number to XMM1, increment, EDX, compare it, should be less than, yes. So now we get the next number, 1.6, and we square that difference, and then we add that to the XMM1. So we keep going through that. The numbers are changing, yes. Oops, I missed it. The standard deviation seems to be 0.265. Let's trap it down here and watch the end of it. All right. So at this point we have in XMM2 this we're going to put in there the decremented value of RSI or ESI. So we get a 9. That's good to see. Then divide scalar double XMM1 divided by that, and our average squared deviation is going to be 0.07025. Then the V square root, you can see, has changed XMM0. So that is the square root of the other number. That sounds good to me. So I think that worked correctly. Now, are there any questions about these basic operations with floating point arithmetic? All right. Then there's a few more things worthy of looking at. With floating point arithmetic, you'll notice I put in here U, ISD and U, ISS. These are for comparisons. The ISD is for unordered comparison. I don't know what the I part stands for. Scalar double. The I must mean something. It's not an integer. And then unordered comparison, scalar single. Now the ordered comparison, I believe, is just COM-ISD. And what I did at the start of doing floating point arithmetic was to use GCC and look at the code that it generated for floating point comparison. It was good enough for GCC to use UCOM-ISD, so it's good enough for me. That was my feeling. A more technical discussion of this is in this documentation of this stuff. An unordered comparison differs from an ordered comparison in not generating an exception for a quiet not a number. And I don't deal with not a number very often, but not a number would be a result like dividing by 0. Now, if you divide by 0, I think you're going to get the program dying. Let's see what happens when we change this code to divide by 0. All I got to do to divide by 0 is pass in a 0 into the average function. That should be pretty easy. Here we go. Tell it to add 0 numbers. It's going to add the first one because I put the test, I think, at the bottom of the loop. Let's see what happens. All right, so we're in here and we've got to do subtraction and XOR, and then we're going to add one number up, increment. It's not less than. We convert a 0 to a floating point number, divide by 0. Come on, divide by 0. I got the stupid thing. Did a, whoa. We got a result that is infinity. We didn't get an error. So this would be an instance of a quiet kind of problem. Or it's not really a number, it's an infinity as the way it prints, but is infinity a number? Anyway, if you do a comparison of a quiet not a number, you don't get an error, like I divided by 0 and I didn't get an error. If you do a comparison with a signaling not a number, that means that the signaling not a number always gives you an exception.
Dr. Ray, I think you might need to go outside your representation range without actually going to infinity to get a not a number. Something you can't represent, but isn't infinity.
Yeah, infinity is what I got by dividing by 0, though I think we generally get an exception when we're in C or C++ and we divide by 0. Is that your experience?
Yes, sir, but I think it's going to, I've seen it throw infinity as well. I'm not sure if that's part of the new compiler or the new 64-bit floating point. And it seemed to me like I did some looking at this not a number business here lately, and it talks about exceeding the representation. I think what they maybe did, and this is speculation on my part, but I think what they perhaps did was make it something easy to label, like if you divide by 0, they're just going to throw you infinity, because that's something that they could code for easily?
All right, let's do a little bit of fun here. We're doing divide by 0. How about we do change the code and make it divide 0 by 0? That seems rude, doesn't it?
Right.
Step into the average function. Okay, not a number. I didn't print it as signaling or quiet, but I got not a number with divide 0 by 0.
Interesting.
With a positive number divided by 0, it makes sense that it would be infinity. A negative number divided by 0 would be negative infinity. But 0 divided by 0, not a number. I don't know precisely how C manages to get the exception thrown, but I'm not getting it in assembly.
Yeah, I would have thought 0 divided by 0 is, well, just kind of 0.
No, it doesn't have the same logic as like 1 divided by 0. 1 is infinitely larger than 0, right?
Right.
But 0, is it positive or negative infinity? It just doesn't make any sense. It's not really infinity. All right, there's a little bit of fun with these unordered comparisons or whatever you do. When you want to compare floating point values, you have to use UCOM ISS or UCOM ISD. And I don't know why, but you have to use a different set of jumps afterwards, because instead of modifying the 0 flag and the sign flag, it modifies the 0 flag if the two operands are equal that you're comparing. Then it sets the carry flag if the first operand is less than the second. If they had done the sign flag the same as with integers, you could use the same instructions. So here you can see we got, instead of jump greater than, you need jump above. Instead of jump greater than or equal to, jump above or equal. And then jump below or equal. Equals and not equals are the same because those use the 0 flag. But the A, which you could just as well use jump carry, but I don't know that there's a jump carry or equal. So a jump above and a jump above and equal, jump below and equal. Those are fine, and then you can negate all of those. I haven't chased down trying to find an answer for why they use the carry flag. It just seems like a pure meanness on the part of the engineer to force the programmer to use different instructions. All right, do we have any questions about floating point arithmetic? We don't have time to do an awful lot of these tests. See if I've got some more instructions documented correctly. How about move scalar double? I've got that in here. It works like moving the other stuff, except that with move scalar double, you use XMM1 or XMM2, etc. Now, if you want to do multiple values and you're going to move, you can either use move APD. The thing keeps jumping off the screen. I believe you're seeing this correctly. All right. Move APD means aligned packed doubles. So if you use an XMM register, you will move two doubles that are back to back in memory. And in the original CPUs, you had to have use this instruction. You had to have the memory on a 16-byte boundary, or you'd get a general protection fault when you executed the instruction. I believe on the Core series CPUs, you won't get the error. And on the original designs, move APD was faster than move UPD, which stands for unaligned. And it doesn't really matter much with the latest CPUs. So I'm going to be using move UPD instead of move APD. So let's go for move unaligned packed doubles. With unaligned packed doubles, I believe you would still want to have your addresses on 8-byte boundaries, natural for doubles, but not necessarily 16. And I guess there would be a V move. I didn't document that. If you're going to do 256 bits in a register, you'd need V move UPD. Let me make sure that's right. Yes. So with V move UPD, it'd be basically the same instruction. You stick a V in front of it, and if you do that and you use YMM1, it will move 256 bits or 4 doubles. And you should use, if you use Y on one, you should use Y on the other. You can use X with the V type instructions, the AVX instructions, or you can use the Y. And if you choose the X, you get half the full size. If you choose the Y, you get the full size. So if you're going to do any kind of packed arithmetic, you need to move packed doubles. So let's, just for fun, do some code in this program. And I'm not going to complete it, but I'll just stick it in here in main. There is a V0 all instruction, which zeroes out all of the YMM registers. And then let's do V move unaligned packed doubles, YMM0 from X. And then V, we can do a V add packed double, I believe, and add that immediately YMM0 from, how about X plus. If we're going to skip past the first 4 of them, it'd be 4 times 8 or 32. So let's see what we get when we do this little bit of code. Zero them all, and then move a number in there, but it's showing us one number. We can choose 4 doubles for the format, and we can see we've got 1.5, 1.6, 1.7, and 1.3. And then we're going to add to that 1.4, 2.1, 1.8, and 1.6. So there we have the sum. Let's make that a little more obvious. Let's do a move. Now we have 2 of these. And let's do V add packed double, and we'll use YMM0, YMM1, YMM2. So we load the first 4 values into YMM1, then load the next 4 values, and then add the 4 together. Now, memory is a lot slower than the CPU. So if you're going to get any benefit from doing anything with these packed numbers, you're going to have to do a fair number of instructions. And computing an average, you're going to be bandwidth limited on accessing the memory. Computing a standard deviation, probably also. I've got code that I did in chapter 19 that computed correlation, and I did manage to get correlation to speed up, sort of, but I think it probably is cheating a little bit. I'm using the same memory repeatedly. So I got it to do the arithmetic quickly, but if I had to load the memory and then do the arithmetic, even that I don't think would let you get close to the ultimate capacity of the CPU. So I've discovered I need to add a few pieces. What was it that I missed? I know I had a problem in it. I didn't have all of the divide instructions. Oh, I don't have the convert instructions. All right, convert and divide. Well, that's probably an introduction long enough for floating point arithmetic. Do you have any questions about any of this before I end for the day? Floating point arithmetic is relatively easy. It's a slight pain if you delve into the packed numbers. For example, if you doing just those packed adds was easy, but you got 4 numbers. How do you get the sum of those 4? You can move them into memory, go through a loop, and add them all up. There is a half add, which will give you 2 numbers. I think it gives you the sum of the first 2 and the sum of the second 2, but there's not an instruction, at least not that I'm aware of yet. There may be one in the most recent CPUs from AMD or something, but not one that's available on most people's computer that will add the 4 numbers that are in the YMM registers for doubles. It would be handy. There is an instruction for a dot product, but it doesn't do the full dot product. It does some multiplication, and then it does like the half add together. So it doesn't complete it. All right, something easy. Floating point arithmetic, yay.
Still, I could see you.
Pardon?
Still, I could see you loading things, say 4 at a time, from memory into a register, doing a packed, doing the packed arithmetic to get the average, and then doing something similar for the standard deviation.
You could do it, but the challenge is unless you've already got that data in cache, the CPU is going to be idle while it's fetching the numbers from memory.
Right, but at least
get 4 floating point results per cycle, or you can actually get more than 4. I think there may be 2 of these pipelines available. So maybe an ultimate thing, maybe you could get 8 floating point instructions per cycle. But you're not going to get that if you have to fetch the numbers from memory.
Right, but I mean, if you got no choice but to get them from memory at some point. I mean, if there are 10,000 values or something like that, you're going to have to go get them from memory anyway.
If you're going to do a lot of work with them, then even if you're doing a handful of different calculations, but they're each kind of small, you could get some speed up from doing it with the SIMD instructions.
Right.
Just depend on it hanging around in cache if the data is not too large. And if your data is large, then the solution, which I probably had me in a class telling you this, you got to maintain the data locality so that you end up needing to break your data into chunks that will fit into cache to do the work on each chunk and then move to another chunk. That's important for a variety of applications. Like if you're doing matrix multiplication, you can do it in blocks, something like 64 by 64 blocks with matrix multiplication. You can get it to go maybe 5 or 10 times as fast, written in a high-level language, because you get to reuse the numbers that are in cache. Whereas if you go through a big array, going all the way across and then all the way across another row, and you're stepping down through the rows of the other matrix, you're going to have the CPU starving from data. But in reality, the value of assembly language for most of us is going to be just to understand how the computer does things, and not to write code that runs extremely fast. Some people will do that. It will be fun.
For me, it's been understanding just how much idle time that CPU has during my code.
Yep.
There
Well,
he is.
I think I've done enough for today. Bye, people out on YouTube, man.
Take care, Dr. Ray.
See you.